Okay, good morning, ladies and gentlemen. Welcome to the International Visiting Lecture. With them is Stephen, the Baptist University Malawi. Welcome to the another one, Mr. Wisdom Kapinga. As a lecturer of the Department of Computer Science, as for the topic today is epidemic modeling with network. And for today's session is being live streamed on the University STEKOM YouTube channel. And now I will read our agenda list of down. First, we will start class presentation delivered by Mr. Wisdom and continue with the Q&A session. And in the next section, we have time for presentation and master disposing. Let's begin. We will start delivered by Mr. Wisdom. The time is yours.
All right. Thank you, Lord. As I've already been introduced to, I'm with Kapinga from Malawi. I work in computer science department here at DMI St. John the Baptist University, Blantyre campus. And today I'm presenting on epidemic modeling with networks. So to begin with, we're going to start with an outline of my presentation. So basically, we'll have an introduction, and then we'll have also a brief background on epidemic models. What are some of the common epidemic models that are used, and then we will now connect these models with now the concept of networks. And of course, I have one example of how modeling is done using the concept of networks. And lastly, we'll have a summary of what we'll discuss in this presentation. So before maybe I go further, I just want to get an assurance that you guys are able to hear what I'm saying. Are you guys able to hear me clearly?
Yes, sir.
All right. Then I can proceed, of course. What is an epidemic modeling? So basically, on top of epidemic modeling, we are looking at approaches where you combine mathematical, statistical, and then also computation tools to study the spread of communicable pathogens or viruses or any carrier of disease in the host populations. So basically, on top of epidemic, we're looking at studying the spread of these diseases that you can infect others by contact or another way. And on the other hand, when we are looking now at combination of epidemics and the networks. So basically, this concept of networks comes from a concept of graph theory in mathematics, whereby you're looking at a set of edges and a set of vertices, where these vertices are sometimes called nodes, and these edges sometimes are called links between these edges. So when you look at that particular system, whereby you have nodes and you have links that connect these nodes, we call this networks. And of course, in computer science, we are referring to them as a whole system of connection of computers, whereby you're looking at a number of computers that are connected together, and then we call them networks. But then in the context of mathematics, we are now looking at these computers as nodes, and we are looking at the links as a connection between different gadgets or different devices. So here we're looking at individuals that are in the population as our nodes, and their contact as the link. If there is a contact between two individuals, then we say that there exists a link between these two individuals. So basically, this is what we're going to use here to say, okay, what is the connection between these networks, the system of connection of devices, and then what is the also connection of if you're looking at epidemics, where we're looking at individuals and their connection. So basically, that's what going to look at in this presentation. Now, to begin with, we are looking at epidemic models. Of course, we have already defined what is an epidemic model, but then for us to understand the whole idea of epidemic modeling, we need to understand that when you look at epidemic models, they do classify every individual into one of these three categories. So the first one, the first category is susceptible. So if you have an outbreak or when you have an epidemic, there will be other individuals who who don't have the disease at that particular time, but there is a chance that they can get that disease. And these individuals that are in this category, we call them susceptible individuals. And as well, if there is an outbreak of epidemic, and there will be other people who are infected with the outbreak. So we call them, we put them in the category of infections. And again, there will be also other people who might also die from the outbreak, or there are other outbreaks whereby after you get infected and then you recover from them, you get immune. So we put these people who got immune from that break or who also died from that break. We put them in a group of recovered. So basically, there are three compartments when we look at epidemic models. And if you're now looking at epidemic models in general, the most used ones are the three, which are SI model, and we also look at the SIS model, and we also have another model, which is widely used as a SIR model. So when talk of SI model, we are just looking at a model whereby you want to model those that are susceptible and they are infected. So you're just looking at the relationship to say, okay, what does it take for one to be susceptible and then infected, and how will the disease spread in that context? And when we look at susceptible, infected, and susceptible SIS model, we're looking at a model whereby you're looking at individuals who at first were susceptible and they got infected, but after got infected, they might heal from the disease. But then after they are healed, they might also they might also be susceptible to the disease, or they might get they might also be in danger of getting the disease again. I mean, the common example of the disease is flu. For example, if you get flu and then
Hello, Novita. Can he start presenting? Can Wisdom start presenting now? Or is it Abdul?
Yeah.
Can he start presenting now?
Oh, yeah, yeah.
Wisdom? Wisdom, are you connected?
Yeah.
Wisdom? Looks like he is muted. So, Novita, are you okay if he starts presenting now?
Yeah, it's okay, sure.
Okay, let me follow up with him.
Yeah, yeah, it's okay. We can wait.
Hello, Briskila. Good morning.
Good morning, Mr. Good morning, Brother Luku. How are you?
I'm fine, thank you. Could you tell Wisdom to start presenting now on the webinar?
Oh, okay. Let me. He already went there. Let me remind him.
Yes, please let him.
Okay.
Let him connect and help him to connect and start presenting immediately.
Yeah.
Please,
Okay.
please.
Okay.
Everybody is waiting for him. Is connected. So I'm following up with Wisdom. He will be connected shortly. So just hold on. Keep on waiting. He'll be connected shortly. Thank you very much.
Again, thank you, sir.
So please, Briskila, can you check on Wisdom, because everybody is connected here and we are waiting for Wisdom. Please check him if he has any problems with the connections. Please check him quickly. I want to know. Thank you.
Yes, sir.
Okay. Hi.
Yes, so Novita, you can welcome him. I think he's now connected.
Hi.
Yes, sir. You can continue this presentation.
Yeah, I'm sorry, I lost connection, and unfortunately, I was not aware that I lost connection.
It's okay.
Okay. So I don't know how far did I go?
You need to connect your presentation, Wisdom.
Yeah, I'm connecting now.
That's better.
I think you're able to see.
So she said that you can start whenever you're ready. So we have been waiting for you. And please start from the first slide and then walk us through. Thank you very much.
You're welcome. Okay, so I don't know if I have already presented this slide or I should start off again. All right, thank you. So this is the introduction of my presentation. So I was saying we're going to look at the introduction, and we're going to look at epidemic models, and then we're going to look at the connection between epidemic modeling with the networks. And we're also going to look at an example. And the last trip, we're going to finish by looking at the summary of what we are going to discuss here. So in introduction, we are looking at epidemic modeling. So when we talk of epidemic modeling, we are looking at a set of approaches where you combine mathematical, statistical, and computation tools just to study the spread of communicable pathogens or in a host population. So here in epidemic modeling, we are just looking at how does a communicable disease spread in a population. So there are, of course, some other diseases which are not communicable, so you cannot put them in this category. But here we're looking at those diseases where which you can infect others by getting into contact with them or by any other means. So when we talk of now epidemics and networks, we are looking at the connection that is there between the concept of networks and the concept of epidemic. So as I've already said, when we look at the epidemic, we're looking at the spread of communicable disease, and you are looking at a group of people where some of them, they have disease and they can infect others. So, and as well, if you look at the concept of a network, this concept of a network borrows its concepts from the graph theory subject, whereby in graph theory we are looking at a combination or a system whereby you have a set of edges and a set of vertices, whereby edges are also sometimes called links. And in computer science, these vertices, we call them devices or computers. And if there is a connection between two devices or computers, we say there is a link between them. So we're looking at a population where there are people who can infect others, and this infection can only happen if these people are get into contact. So basically, that's the whole connection between epidemics and the networks. And now we're going to look at the epidemic models. But then before we look at the frequently used epidemic models, we need to understand that when we are doing epidemic modeling, we categorize individuals in the population into three categories or three compartments, whereby we have susceptible individuals, infectious individuals, and the recovered individuals. So susceptible individuals, we're looking at these individuals who are in danger of getting infected in the population. For example, I might be healthier today, but if there is an outbreak, I might as well be in danger of getting that that pandemic. So that's about susceptible. And when talk of infections, these are now people who are infected with the outbreak, and then recovered. These are now individuals who are immune or who got immune after getting infected, or who are recovered, who have recovered from the disease. And as well, these are people that cannot get infected again because they have recovered, and then they can no longer be susceptible. So when we look at now three frequently used epidemic models, we're looking at the susceptible and infected. So in this model, we're just looking at okay, how many are susceptible and how many got infected from the whole population. So this is the simplest model of all. And we're also looking at the other model is susceptible, infected, and susceptible, which in short we just call it SIS model. So in this model, we're looking at these particular diseases whereby you can be susceptible today, and then you get infected. After getting infected, you can get healed, of course, but after you get healed, you again ended up being in danger of getting that disease again. So the most common example of this particular disease is flu. So if you got flu, you can heal today, and then you also be in danger of getting that flu again. And the last model, the last frequently used model is the SR model, whereby in this model we're looking at the where you got susceptible, or you got infected, or you got recovered, and after you get recovered, you got immune, or sometimes there's a possibility that you might also die from that particular disease. So we need to remove that proportion from the population, so that we have a clear picture of who remains. Who are people who are remaining that are susceptible, and who are remaining that are infected. So basically, these are the three frequently used models. But then let's now take a quick look of what are the models that we use when we are trying to model the epidemics. So when talk of SI model, this is the model that we use. And I was saying, if here we have beta, and then we have K here, and then we have I, and then we have 1 minus I. So basically, when you talk of beta, this is the probability or the likelihood of one getting infected from someone who has already been infected. So if you're in a population and then there's an outbreak, what is the likelihood that you get affected? So we represent that probability by beta, and this angle K, we refer to it as a number of contacts each individual has. So I was giving an example to say, if you're, for example, if you're in Malawi and then there is an outbreak here in Malawi. Now we're looking at what is an average of each of contact of each individual. For example, you're looking at if I go out of my house, how many people do I get into contact with? And you're also looking at another person. What is the number of contacts? So you take all these contacts and then you take the average. So that average is the one that you put here to have an idea of how many people an individual in Malawi contact per day. And this I here, we're now looking at the proportion of people who got infected from the disease that we are trying to model. So if the whole population is, let's say, 10 people and only 2 are infected, then the I here will now represent, let's say, 1 over 5, which is the same as 2 over 5. And the 1 minus I now represent the proportion of the whole population of people who are not infected. Because here we're saying I is the proportion who got infected, and if we subtract by 1, then we're remaining with people who are not infected, but maybe these people are now susceptible or they're in danger of getting infected. And I was also defining, characteristic time to say this is a time whereby you're looking at how long does it take for an infected person to infect a healthy person or someone who is in category of susceptible. So this characteristic time is given as tau, which is equal to 1 over beta k. And the basically, when you look at the beta, which is the probability of one getting infected, and the k, which is the number of contacts. So if you multiply beta times k, this gives you actually the transmission rate, or the rate at which the disease will spread in that population. And if you take the inverse of that, which is 1 over the transmission rate, that will give you the correct time, which is the time an individual it takes for an infected person to transmit the disease to a healthy person. So basically, these are the most important concepts when we look at the SI model. And now, if we quickly look at the SIS model, we are now looking at if you see the model here, we are looking at what we have in the beginning here as the same as what we have in the SIS model. But we are now including another component, which is the mu I, where mu, we refer to it as a recovery rate. The rate at which people are recovering from the disease. So when we look at SI model, we are actually not concerned of how many people are getting healed. So in the SI model, we're looking at people who are infected and some who are susceptible. But in this model, we have a chance to say, okay, this disease people can get healed, and we are including this component in this model. So actually, as I've already defined, to say mu is the recovery rate, the rate at which people are getting healed, and we have already defined the I to say this is the proportion of people who are infected in the whole population. And the characteristic time for this model, SIS model, is given as 1 over mu R0 minus 1, where actually R0 is given by you divide to say transmission rate divide by the recovery rate. So that will give you the R0, which is also defined as a reproduction rate. The rate at which new infections, R0 is defined as the number of new infections each infected individual causes under ideal circumstances. So we're looking at if I am sick, how many new infections can I cause? And that is given by the transmission rate. You divide it by the recovery rate. And if you look at it now, the characteristic time is given as 1 over mu, which is the recovery rate, and then you multiply by reproduction rate minus 1. So that's it about SIS model. And if you're now looking at the SIR model, we are looking at, if you're looking at how to get susceptible individuals in the population, then we use this formula to say minus transmission rate, and then I, of course, here we have also introduced another variable, capital I, whereby capital I, you're looking at the total number of people who have got infected, regardless of whether they have healed or they are still infected. And these are here, we are now talking of those who have recovered, to say, okay, if you're looking at the total of who got infected, what is the number of people who got recovered or got immune or they are dead? And we have also to subtract with the those number of people who are still sick. So this will give you the total number of people who are susceptible at that particular time. And for you to get number of people who are infected at that particular time, then you need to include recovery rate. You multiply it with the infected with the proportion rate, and then you also have to have like a transmission rate multiplied by I with the capital I minus R minus I. So this will give you a number of people who are infected at that particular time. And if you look at the number of people who got recovered, or maybe they have removed from the population, then you're looking at multiplying the recovery rate multiplied by the infected rate. Now, if you're now looking at the characteristic time of a SIS model, it is actually categorized into two, depending on whether tau is greater than 0 or whether tau is less than 0. And I have to say here to say that the tau here that we're talking about is the same tau that we looked at when we were looking at the SIS model. So we still use the same formula, but then we say this pandemic is in endemic state when tau is greater than 0. For example, when you have a scenario whereby the recovery rate is less than the transmission rate. So if you have less people recover from the pandemic, and the transmission rate is high, then the disease is in endemic state, and the crisis time is obviously greater than 0. But then we have also another state, which is a disease-free state, and this state comes when you have the recovery rate greater than the transmission rate. I mean, for example, if you're looking at a scenario whereby there are more people who are getting healed from the disease, and there are less who are getting infected from the disease, then obviously you get at a state whereby the disease will die. So we have these two states, which are actually determined by what is the value of tau, and in terms of is it greater than 0 or less than 0. So that's it about epidemic modeling in general. But then why are we saying epidemic modeling with networks? So as I've already said, this concept of networks in epidemic is coming in because we are all looking at the only possible way that you can infect the other person is that you come into contact with that person. For example, there is a link between an infected person and you as a healthy person. That's the only possibility that you can get infected. So we say individual with more links have high chance of getting infected. For example, if I get into contact with many people, then it means I also have a high chance of getting infected. Or if sometimes I'm the one carrying the pathogen, then I can spread that pathogen very quickly because I come into contact with the many people. But then the weakness of the models that we have seen before is that you only we look at an average of contact. So if, for example, you're looking at this country to say, okay, in Malawi, what is the average of contact of people? So you can give it to say 10, but doesn't necessarily mean that everyone in Malawi, they come into contact with 10 people. So that's where now the concept of networks comes in to say we now want to look at the exact number of contacts that each individual has, without in contrast to looking at the whole average of contact of people in the population. So epidemic modeling with networks distinguishes nodes based on their degree. So actually here the degree here is the number of contact that every node or every individual has. So this process we call it a degree block approximation. So what actually happens here is this. So we're looking at different people having different number of contacts. So what we do is we group those people together, the ones that have the same number of contacts, we group them together so that we model them, we develop a model for this group, and then we also group another group whereby you are looking at those people who have again the same contact, and then you also develop a model for that, so that in so doing you have a model that tells you exactly to say these people this group of people, they do get into contact with this number of people, and from there you can have a very accurate epidemic model that will accurately predict characteristic time or the number of infected people in the population, and that will also maybe improve on the decision making, because you have the exact figures in terms of how the epidemic is going on. So basically, this is the degree block approximation that I was talking about. So you see that, okay, this is the population. These are a number of individuals in the population, and these are the contacts to say this guy here comes into contact with this guy. And so you see that this block here, we're saying K, which is the degree, is equal to 4, which means every person in this block, they do have 4 contacts, and everyone in this block, they do have two contacts, and here they all have 3 contacts. So as I was saying, we have the model for this block, and you have a model for this block, and you have a model for this block. So we will do that for every degree that you have in your population. And now we are now looking at that concept of a network that we have just introduced, and we will now go back to those epidemic models. But then now we are now looking at the same models, but with a concept of networks, whereby you're looking at the exact degree of each individual. So if you're looking at the proportion of number of affected individuals with a degree K, so for example, if you're trying to model SI model in this block where K is equal to 4, then here you have to say K is equal to 4. Now that the model will be given by DIK, where K is the number of contacts, and then you have beta 1 minus IK, and then you multiply with K. In that as well, you see that this model will be the same as the model that we looked at, but we have also added this variable. So I'll call it theta K. So theta K is the fraction of affected neighbors of susceptible nodes with the degree K. So for example, if you're looking at this block, so you're looking at okay, what is the fraction? What are the number of infected neighbors. So if this is infected and then this is infected and they are all connected to individuals in this block, then this number theta k will get its number from those number of infected neighbors of susceptible with the degree k. And as I already said, ik is the number of infected nodes with the degree k. And now the characteristics time will now be given as tau, which is a number of contacts, and then you divide it by beta, which is the likelihood of an healthy person get affected. And the k squared here, we're now looking at the variance of the nodes of the degree k. So actually, this model predicts accurately as compared to the SI model, and the characteristics time here is also more accurate as compared to the characteristics time that we looked that we have discussed before. Now, when we are also looking at the SI model with networks, we also have to look at the nature of the networks that we have. So basically, the nature of the networks that we have, there are two of them. So the first one is random networks. So with random networks, we still consider the number of contacts. We still take the number of contacts using average. So if your network is of random network, then it doesn't make any difference when you compare it with the normal epidemic modeling without epidemic modeling without networks. But when you look at scale-free networks, so actually when we are modeling using scale-free networks, we use what we call power law exponent, which we use to determine the characteristic time. And basically, you can predict when the power law exponent is greater than 3. Sorry, the power exponent is greater than 3. So, but then if it is less than 3, then the prediction doesn't actually bear any fruit. So you cannot, you cannot predict when the gamma, which is the low power law exponent, is less than 3. So basically, again, when you look at the SI model with networks and you want to predict, it does actually depends on the nature of your networks. And now let's quickly look at the SIS model, and of course we're going to look at also vanishing epidemic threshold. So if we when we look at the SIS model, this is the model that we use, and I think many of these concepts we have already explained them to say this is the fraction of susceptible individuals who are affected in a particular block, and the new here is the same recovery rate, and the high IK is number of infected people in a particular block, or number of infected people with the degree K. So for you to find the number of people who are infected and they have degree K, then you have to use this. This model, and this, as I've already said, gives you the accurate results. And the characteristics time for this model is given as TSIS, and then you have number of contacts. You divide it by beta, which is the probability of a healthy person got infected, and you have the variance of the nodes in a particular block, and then you also multiply with the recovery rate multiplied by the contact, the number of contact, which is a degree in this particular case. So the spreading rate here, or the transmission rate, is given by beta, which is the probability of one getting infected, and then you divide by the recovery rate. So you see that if this mu here is large, then it means this lambda here will be very, very small, which will mean that the degree, I mean the rate at which the disease is spreading is very low, and as a result, the disease will die quickly if this mu, the recovery rate exceeds more with beta, which is the transmission rate. Now, as I've already said, when we are looking at SIS models, epidemic models with networks, we still have to look at the nature of our networks, or the nature of our graph. So, in random networks, the epidemic threshold is given by lambda c, which is equal to 1 over k plus 1. And maybe I do not define what is an epidemic threshold. So this is a point whereby the number of people who are getting infected and the number of people who got healed is the same. So we're looking at it whereby the point whereby the disease stopped to spread, like not more people are getting infected as compared to people who are getting healed from the disease. And when we are looking at now a scale-free networks, then the epidemic threshold is given by this formula, whereby you're looking at the degree, and then you divide by the variance of a degree in that particular block. So if lambda here, where lambda we have already said, we have already defined in the previous slide to say is the spreading rate. So if the lambda is greater than the threshold, then it means that the pathogen will spread, because it means there are more people who are getting infected as compared to more people who are getting healed from the disease. And if lambda is less than lambda c, which is the threshold, then it means that the pathogens will die out, or the pandemic will come to an end. And now let's, after we have discussed epidemic models with networks, let's now quickly look at this example, whereby we have taken this example from this guy who used Markov chain with 2 states to model. If you're looking at the using Markov chain with 2 states model, then we're just looking at people who are not sick and the people who are sick. So the 2 states that we are going to use in this model is that to say we're looking at people who are sick and people who are not sick. So, for example, if you're looking at the people who are not sick, then you're going to have 1 minus PIT, and then you use this this model. So we have PIT is the probability of node I get infected at time t. So we're looking at the probability that if you're looking at the individual I in a particular block, what is the probability that that individual will get infected? And this guy is the probability that node I will not get affected from its neighbors. So if you're using this model and we try to do simulations, for example, I took a network where there was 34 individuals, and if we use that this model and run the results, then we're going to see that depending on the beta and gamma, we do have 2 different thresholds. For example, when beta is equal to 0.24 and gamma is equal to 0.8, then you have a threshold there around 19 or 20, whereby you are expecting that the disease will die after maybe 20 people have got infected. And you see that that threshold will reach maybe after 10 days, to say the disease will actually maybe die or will stabilize after 10 days. And when beta, now if you just interchange beta and gamma, and then that will now give you a threshold of 33.84, whereby we are saying here the population is what is 34, and we are saying that the threshold is 33.84, which means almost every individual will get infected. And maybe I did not mention what is beta and gamma in this particular case. So here, beta and gamma, we are looking at the transmission rate and the recovery rate. So in this sense, then gamma is the transmission rate, and beta here represents the recovery rate. So you see that here the transmission rate is smaller as compared to not transmission rate, but gamma is gamma is the recovery rate, and beta is the transmission rate, as we already discussed. So you see that if you interchange the beta and gamma, then you're going to have different results altogether. So here it means in this particular case, then it means the transmission rate is greater, as you'd see that beta here, which is the transmission rate is greater than the recovery rate, which is 0.24. This is why you'll see that the epidemic epidemic threshold reaches at a high speed. For example, maybe after 5 days or 4 days, everyone got infected. While here, the transmission rate, which is beta, was smaller as compared to the recovery rate, which is gamma. So you see that here, the threshold is 19, which means there will be other people who will not get infected, and the threshold will be reached maybe after 10 days, something like that. So some of the limitations of epidemic modeling with networks is that data variability. For example, it is very hard for you to get an information of how many people every individual in a community get into contact with. So it is very hard to get this data for you to moderate. And we also talk of network dynamics. So here we're looking at there are different networks. For example, you'll see that every district, for example, maybe every part of Malawi will have their own nature of the network. So you see that maybe if, the other part will have a scale free and the other part will have random network. So there is a lot of dynamic on top of networks. And we also talk of heterogeneity of nodes. So
Are you experiencing problems? I think. Wisdom, are you experiencing connection problems?
no, I think I'm connected.
Oh, you are back now. Thank you. Thank you. Proceed.
Yeah, so I was just concluding to say, epidemic modeling with networks offers a powerful tool for studying the spread of communicable diseases. And as I keep on saying, to say that if you use traditional epidemic modeling, of course you get the results, but those results, they are somehow lack accuracy as compared to the results that you could get from using epidemic modeling, whereby you get the information of each individual. Where now that the concept now that we have discussed here, whereby you're looking at the concept of network and then you combine with the epidemic modeling, that will give you a very accurate results, whereby you are going to have a clear date of where the epidemic will end, and you also have a very accurate characteristic time of a pandemic. So this is the end of my presentation, and thank you for listening.
Yeah, before you leave, there are usually some questions from the audience. So I think Novita is going to guide us, or Abdul, on how you have to address the questions, one or two. Novita or Abdul?
Yes, sir. Yeah, for our participant, if you have any question for the speaker, please add them to the chat, or you can raise your hand. We will wait until 2 minutes. Thank you. Hello, sir. Hello. We have three
Yes,
questions.
Wisdom, you can pick up the questions. There are three questions.
I lost my network maybe when the questions were presented, so I'm sorry if you may repeat questions.
They are written, so you can check on the comments section. You will see the questions there.
Okay, right.
So you can address them one by one.
All right. There's nothing in the chat. I don't see anything in the chat actually. So, no.
You can see the chat. The chat. The questions are on the chat.
Yeah, I can see the chat. Yes,
Yeah.
I can see the chat.
Yeah, please try to respond to those questions on the chat.
Oh, okay, I can. I'm able to open the chat, but I can't see any question. I don't see any question.
No, I will read it. It's okay.
Maybe someone may just copy and paste it again on the chat.
Pardon?
That would be.
Pardon?
He says that someone can copy the question and show it on the screen because you cannot see the questions on the chat.
I will read it.
Okay.
Our first question, we
I think
have.
I've seen one.
So, Wisdom, the first question is saying, what are the key advantages of using network-based models over the traditional compatible models?
Okay,
That's
so
it.
I can now see it. So,
Okay.
what are the key advantages of using network-based models over traditional compartmental epidemic models? So, as I've already said, the traditional method considers that every individual in the population has the same number of contacts, right? Which is not actually the case in a real setup. For example, I was saying that you can model to say, okay, in Malawi, the average of contacts in Malawi is 10, but that doesn't necessarily mean that I have 10 contacts. For example, I can have less than 10, or I can have more than 10. So because of that, it doesn't really give you an accurate result in terms of finding the number of infected people, or also get the characteristic time of your model. So if you use network in labeling, you are now considering the actual number of contacts of each individual. So as I was saying, you put them together and then you model that block that has the same number of contacts. So this gives you a very accurate result as compared to just make an assumption to say everyone has the same contacts. So the most advantage of using networks-based models is it gives you a clear picture of what is really happening in the population. So, and then the other question is, how does the concept of net centrality influence the prediction of epidemic spread in a network? So that's also brings back to the previous question to say, if you're looking at a non-centrality, then you're looking at a node which is somehow connected to many nodes, or there is a shortest path in terms of connection between that particular node and another node in the population. So you see that if this central node gets infected, then it means many nodes will get infected as well. So this also actually helps in, for example, if you know that if you know the nature of your network in the population, then you know exactly where you can stop the spread of the disease, because we know that if an individual is highly contacted with other people, then this individual will spread this disease very fast. So when avoiding the spread, you will know exactly of who to focus on. For example, the symptom that you have asked here to say, okay, if you are to stop the spread of this disease, then let's consider these particular people, because they're the ones who are going to have the high chance of spreading the disease. So the concept of centrality of the node helps as well in avoiding the spreading of the disease, and at the same time, it also influences the spread of the disease in that way. And now talking of the prediction, to say how does it influence the prediction? As I've already said, in the epidemic modeling with networks, you group the nodes together. I mean the nodes with the same contact together. So when you are modeling them in their respective blocks. So this actually gives you a great picture to say, okay, this block is going to infect others in this particular way, and this block is going to infect others in this particular way, because you consider the degrees, and you also consider their variance in terms of other infected nodes that are connected to that particular block. So I think that was the second question, and the other one was to say how can advances in machine learning or AI improve the accuracy of epidemic modeling with networks. So about that, we know that we are living in AI, and if you're looking at improving the accuracy of epidemic modeling with networks, as I've already said, this if you are predicting using networks, you're going to produce a very accurate results. And maybe how will AI improve on that particular results is that maybe you are going to develop models that are I mean, you can develop them easy using AI, and you can also deploy those models using AI side. So I don't know if I've answered your questions, or there is any other clarification that you make.
Because someone else asking the question. Okay, I guess someone else asking again, chat. Thank you for your answer. I think it's very clear answer from Professor. Yeah, before we close the session, for all participants, please open your camera and we will take a picture on the comment screen. Okay, 1, 2, 3. Okay, another 1, 2, 3. Thank you. Thank you for your team cooperation. Finally, we come to the visiting lecture today. We would like to thank you for Mr. Wisdom for the wonderful information and sharing your day. We hope this information will be beneficial for our participants. At least we hope for collaboration in the future. The group can sit in the for today and here. This is thank you and please stay. And bye.